Okay, we're going to continue on here, and like I said, we're going to lecture into a little bit here of not sure how little, we'll see, of chapter 8, which is gases. So let's get into funness of gas. So as you are probably aware of, obviously in the gas state, things have completely broken apart from one another. They're basically flying around. And as they're flying around, there are collisions that occur. And really, the number of collisions really correlates to the pressure that we associate with gases as they collide with the container. The more collisions that you have, usually the greater pressure that you are associating with those gases. Obviously, the lower the number of collisions, the lower the pressure that we associate with them. Now, let's talk a little bit about some substances that basically exist as gases under sort of normal conditions. And when we talk about kind of normal conditions of pressures and temperatures, sort of like room pressure and room temperature, that is 1 atm, which is an atmosphere, and that is a unit of pressure. And usually 25 degrees Celsius is kind of the standard temperature that most things are sort of recorded at. So if you, for example, look at a table in a book of some values like delta H values or thermodynamic type values, they're usually done at 25 degrees, which is sort of considered roomish temperature. But definitely for sure, they're done at 1 atmosphere, and 1 atmosphere is what's referred to as standard pressure. And that's usually what things are done. Under those normal sort of conditions, ionic compounds, which obviously are metals and nonmetals and held together through positive, negative ions coming together and attraction, those things are held together by those really strong electrostatic attractions. And under these conditions, they typically do not exist as a gas. So if you have some type of ionic compound, you could heat the crap out of it and it's not going to go into the gas phase. It pretty much will start to melt before it will go into the gas phase. And again, some of you maybe witnessed that in some of those earlier experiments, especially maybe like experiment 7, where you kind of evaporated off all the water and you're left with sort of a ionic solid residue there. It never completely just evaporated off. There's always some type of ionic residue still in your actual evaporating dish. So because they're held together by super strong forces, they typically will melt before they'll even think about going into the gas phase, and they typically will not go into the gas phase. Now, when we talk about molecular compounds, they are a little bit different. Molecular compounds, obviously, like we talked about with bonding, are like some of our nonmetals together where we have sharing of electrons happening, some covalent type bonding. And some of these things are gases like carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, and methane, which is our guy right here, are gases. Methane, again, is what comes out, obviously, from your Bunsen burner there, and usually very flammable. So a majority, though, of molecular compounds are liquids and solids. And one of the major sort of differences between sort of a molecular compound and an ionic compound is it is really a lot easier to kind of turn a molecular compound into a gas than it is an ionic compound. And a simple example of that is something we're all familiar with, which is water. Yeah. So if you have water in the liquid state, because water is polar, it is held together by what is referred to as an intermolecular force. So the positive side of one water is attracted to the negative side of another. This does what is known as hydrogen bonding. And hydrogen bonding is a intermolecular force. So an intermolecular force is one that basically holds this molecule together with another. So one whole molecule held together with another is an intermolecular force. They are all, as we'll talk about in a later chapter, they're all basically a simple interaction of the positive side of one molecule is attracted to the negative side of another, and that's the force that holds it. So something like water is held together by a relatively strong type of intermolecular force, but it is much weaker than an intramolecular force. And an intramolecular force is the force within just one molecule that holds it together. So in the case, if you just took one water molecule, that is the sharing of electrons there between the oxygen and the hydrogen. The covalent bonding is the intramolecular force. And we know that this happens because when you heat water to make pasta, it is this bond between the two water molecules that breaks first, and that allows those water molecules to go off into the gas phase, and you get your water to start to boil, and you get steam, which is still water. If it was opposite and the intramolecular force was weaker, when you would go heat up your water to make pasta, you would start breaking these bonds, which probably wouldn't be so great because then you start making some hydrogen and oxygen gas and maybe not get to the pasta part of the evening if it was the opposite here. So intermolecular forces are always much weaker, and that is basically how molecular compounds are held together by those kind of intermolecular forces. So they're much easier to break apart from each other, molecule away from another molecule, to create gases. Some of these things, for example, like methane, are held together by super weak forces, so weak that they just naturally come as gases, like again coming out of there. A lot of organic molecules are held together by really weak intermolecular forces, which is why a lot of the kind of early organic molecules, things like methane, propane, butane, ethane, they're all gases because they're, you just look at them wrong and they'll just hop into the gas phase. And that's why they're also very volatile as well, which means they could go from liquid to gas super easy. It doesn't take a lot of convincing for them just to kind of break apart and go away. Water is a little bit different because it is a stronger intermolecular force, so it takes a little bit of convincing up to about 100 degrees Celsius to get it to kind of break apart from each other. And that's definitely not the case with things that are held by weaker forces. So the general rule is the stronger the attractive forces between molecule and molecule, the less likely you would find that thing under normal conditions in a gas phase, as opposed to obviously if they're held together by really weak forces, they're going to go into the gas phase very, very easily. So substances that are found as gases, those are our diatomic molecules we've talked about previously, our H2N2O2 F2Cl2. Ozone, which is O3, is a gas. And then clearly our noble gases, which are monoatomic. They basically come as one. They're fairly unreactive as well. They're chemically inert. So on the periodic table, obviously, these are our gas guys here under normal conditions. Now, gases basically assume the volume and shape of their container. And gases are the most compressible state of matter. You try to compress a liquid too much, you make a mess. It goes all over the place, right? But gases you can kind of compress pretty well. Gases will mix evenly and completely when they're in the same container. So they are flying around. And one of the things that we will talk about is ideal gases. And most of the time we deal with ideal gases. And that's actually one of the things that makes something an ideal gas is even though you may have a mixture of gases and they're flying around the same container, what makes something sort of an ideal gas is the idea that it is assumed that they will not interact with other gas molecules. So it's almost like they're in the container by themselves in an ideal situation. And that's usually the situation that occurs under normal sort of pressures and temperatures, that there really will not be too much interaction happening between different gas molecules in the same container. Gases have much lower density than liquids and solids. We'll talk about density in this chapter. Unlike solids and liquids, where we typically give density in grams per milliliter, for gases we typically give the density in grams per liter. So we typically will give the density of a gas in those units rather than solid and liquid, which is grams per milliliter like we normally would. Pressure obviously is an important unit in gases. And the big three of units is typically these guys here. 1 atmosphere is equal to 760 mmHg. That stands for millimeters of mercury. And that equals 760 torr. 1 millimeter of mercury is equal to 1 torr. It's a 1-to-1 conversion between them. Also, occasionally, 1 atmosphere is 101,325 pascals or 101.3 kilopascals. We don't deal too much with pascals or kilopascals in here, but maybe in physics and stuff like that, you might come across that. Other units that you may also be familiar with, right? PSI, pounds per square inch. 14.7 there is a relationship. Also, maybe as well a bar. Yeah, it's another unit of pressure. And it's very similar to an atmosphere. It's like 1.01 to 1. So they're almost equivalent to each other. They're slightly different. That means 760, though, for our big three here are typically an important number. So obviously, if you have millimeters of mercury or torr, and you want atmospheres, you need to divide by the 760, and that will turn your number into atmospheres. If you have atmospheres and you want either millimeters of mercury or torr, you need to multiply by the 760. You got to multiply. Here you got to divide. And that will give you millimeters of mercury or torr, which again is basically the same sort of unit as well here. This over here is our classic barometer, and a classic barometer was filled with mercury and it has a glass tube in it. And as the atmospheric pressure exerts on the pull mercury within the barometer, the mercury in the tube rises. And typically on these things, there would be a classic ruler. And it would either be a lot of times inches, centimeters, or millimeters. And you would measure the mercury level in it. Hence the name millimeters of mercury, basically, is where that comes from. Again, it's basically the measurement of the mercury in the column. A reminder, as we might have talked about it, mercury is a weird thing in the sense that its meniscus actually goes the opposite way. And if you ever come across one, which you probably won't because they've taken it out of all colleges because it contains mercury, you usually read the meniscus from the top of the meniscus. And that's because mercury actually is more attracted to itself than the glass container or walls of that tube. So it comes in on itself. So you actually read from the top of a mercury meniscus there. Where does the torr come from? Well, it comes from the guy who invented the barometer, Torricelli. So that is where the torr sort of unit comes from. The guy's name that invented the barometer. All right. So obviously, as you travel away from sort of sea level, you can see the pressure starts to decrease as we go higher up there, right? I'm assuming perhaps why they pressurize planes when you're up there, up high, so there's no issues or anything like that. This is a manometer, which is used to measure gas pressures. And there's one here under a vacuum, basically means it's sealed to the outside there. So there's no atmospheric pressure involved there. So if you have a gas, it's going to move the mercury. And one way that you can sort of figure out the pressure is by measuring the height of the mercury in the column. In this case, the pressure of the gas would equal the height of the mercury in the column. Now, if you have more of an open system, you then would have some atmospheric pressure as well involved. And you would do the same thing. The pressure of the gas would be the height of the column plus the atmospheric pressure as well. It does need to come into account when you're dealing with that, rather than the kind of the closed system that you have there on the left. So when we talk about relationships between what's happening and pressure and stuff, there's three variables that we deal with in gases usually: pressure, volume, and temperature. And the first relationship we're going to talk about is from our friend Boyle and Boyle's law. And Boyle dealt with the pressure and volume relationship. He held temperature constant. And if you kind of take a look here, you can see in these apparatus here, we have 100 milliliters of volume of gas, and our pressure is here. We then drop the volume here to 50, and we actually see a rise in the pressure. And we drop it even more there, in this case to 33, and we see an even bigger rise in the pressure. And what Boyle sort of discovered was, as the pressure goes up, the volume goes down, sort of an opposite relationship there, and vice versa. As the pressure goes down, the volume goes up. So if you just think about, maybe logically, if you have a really small volume of gas, those gas molecules do not have to travel very far to start colliding with things, right? So that's going to definitely increase the number of collisions. And the result of that is we will see the pressure start to go up. As opposed to if you gave those same gas molecules a little bit more room to fly around in. And if you increase the volume, it's going to take longer for those collisions to occur. And that means that you actually will end up with less collisions. The result of that is less collisions. You'll start to see the pressure come down. So as one goes up, the other comes down, is the relationship that we see here with Boyle's law. Question on that there. And that can be graphed here. As you can see here, these are two sort of graphs for Boyle's law: larger volume, lower pressure; smaller volume, higher pressure. One of the relationships here that we see, pressure is proportional to 1 over the volume. And one of the relationships we see with Boyle's law is, if you do an experiment and take a bunch of pressure and volume measurements, if you take the pressure and volume measurements that go together, you will end up with a constant number. And that is sometimes referred to as small k, or the proportionality constant. And no matter what you do, the pressure, volume, and a Boyle's law relationship, if you multiply them together, will always be the same. And because of that, you could set basically two of them equal to each other, and we get our classic Boyle's law formula, which is P1V1 is equal to P2V2. Once again here, this is at constant temperature. The unit of pressure does not matter as long as they are the same on both sides, so they could be any unit of pressure you like. Volume here, units on both sides, also doesn't matter as long as they are the same on both sides. So they got to be the same on both sides. And again, the relationship we talked about there: pressure goes up, volume goes down; pressure goes down, volume goes up here. Any questions on that one there? All right, so let's take a look at one here. A sample of chlorine gas occupies 946 milliliters at a pressure of 726 millimeters of mercury. What is this pressure if we reduce the volume to 154 milliliters? Take a couple minutes to just pull out the information. So a lot of times you can kind of see the formula that you need to use. Clearly, at this point, we only have one formula. But if we kind of pull out the information here, we have a volume that's 946 milliliters. It has a pressure of 726 millimeters of mercury. We're looking for another pressure, and it has a volume here of 154 milliliters. So, it kind of points in the direction, hopefully, of Boyle's law, which obviously deals with those sort of values, our variables. Here, we just need to make sure units are the same, so our volume units are the same. Our pressure is in millimeters of mercury, which just means when we solve for it, it will be in millimeters of mercury. You could call these guys ones. You could call these guys twos. It really doesn't matter as long as you keep the numbers that go together together. But typically people just kind of go how it's written in the problem. So here we would be solving in this case for P2. And again, if you're not sure how to rearrange some of these equations, opposite locations, although they are not written as a fraction, you can put them over one, and this guy, when it goes across the equal sign, ends up in the opposite location on the bottom, and that would get you P1 V1 divided by V2 is equal to P2. Putting in our numbers here, we got 726 millimeters of mercury. Our V1 is 946 milliliters, and our V2 154 milliliters will cancel, going to leave us in millimeters of mercury. So we got 726 times 946 divided by 154. Gonna get us here 4460, we'll call it, millimeters of mercury in this particular case. First off, any questions on that calculation? Understanding the relationship of what should happen also can help you, just in case you maybe invert some numbers. What we see here in terms of our volume is going down, and that means that our pressure should go up, and it definitely did go up from 726 to 4400. So we did at least see the right sort of situation that should occur in this particular problem. Yeah. Any questions on that there? All right, let's take a look at another one here. An inflated balloon has a volume of 0.55 liters at sea level, which is 1 atmosphere. It rises to 6.5 kilometers, where the pressure is 0.4 atmospheres. Assuming the temperature stays constant, what is the final volume of the balloon? Okay, so once again, just pulling out the information, we got a volume 0.55 liters. 1 atmosphere is a pressure. 6.5 kilometers is useless information. Pressure here is 0.4 atmospheres. And our volume here is what we're looking for. So again, you could hopefully be able to kind of see Boyle's law sitting there. I'm just going to call again these guys ones, these guys twos. And in this case, our pressure units are the same, so we don't have to worry about converting them. If they were different, again, it doesn't matter what unit you convert it to, they just need to be the same in this case. So our P1 V1 equals P2 V2. We're going to solve for V2, so we're going to send P2 to the other side. That will give us V2 is equal to P1 V1 divided by P2. Putting in our numbers, P1 there is 1 atmosphere. V1 is 0.55 liters divided by our P2, which is 0.4 atmospheres. Here, the atmospheres will cancel. That is going to give us our volume in liters in this case. So 1 times 0.55 divided by 0.4 looks like a volume here of 1.4 liters would be where we would end up. Again, if we look at what's happening here, the pressure goes from 1 atmosphere to 0.4. Pressure is going down. That means our volume should go up. And it went from 0.55 to 1.4. So at least it went in the correct direction based on what should happen in this case. Any questions on that one there? All right, so Boyle's law, P1 V1 equals P2 V2, constant temperature situation. The next relationship we're going to talk about are kind of two. That is our friend Charles' law. And Charles' law basically dealt with volume and temperature relationships. And it held pressure constant. And one that's similar to it is basically our friend here, Gay-Lussac's law. And dealt with pressure and temperature. and held volume constant. So if we take a look at these things, we'll start with Gay-Lussac's law. If I have a container where my volume is fixed, so that means obviously here there is not going to move our volume. If I increase the temperature, my gas molecules should definitely start to fly around a lot faster, right? They're going to gain energy, and that's going to make them move a lot quicker. Like if they light a fire underneath you, they used to say, right? It'll make you move faster. And because of that, that is going to cause a lot more collisions. And that means that we would expect to actually see our pressure also start to increase in that case. Opposite is true if we take our same sort of container here and we got like a fixed volume of gas. And again, if we lower the temperature, what's going to happen in this particular case is as the temperature lowers, our gas molecules will start to fly around slower because they're going to have less energy. And because of that, it's going to take longer for collisions to occur, and we will actually have less collisions. And the result of that is the pressure will go down. So in the case of Gay-Lussac's, because of the constant volume, we actually will see as the temperature increases, so does the pressure. And as the temperature decreases, so does the pressure as well. Now, if we take a look at our friend Chuck's law over here, or Charles' law, if we have a movable, our non-fixed volume, we will see some other things occur. And if we take this situation and we increase the temperature, as we saw over there on the right-hand side, and the volume remained the same, we would expect the pressure to start to increase. But in the case of Gay-Lussac's, I'm sorry, in the case of Charles' law, where you want the pressure to remain constant. So if we increase the temperature and we want to keep it at constant pressure, the only way for that to happen is we would have to increase our volume. So we will see an increase in volume, and that increase in volume will compensate for our gas molecules flying around faster, and it will give them more space to fly around in and actually keep the number of collisions relatively constant. And that is what's going to keep the pressure constant in this case. It is the adjustment of the volume. So in this case, because those gas molecules are going to be flying around faster, we want constant pressure. We need to actually give them a lot more room to fly around in to maintain the level of collisions. Same deal here. If we started with that guy and we lowered the temperature, our gas molecules, like we saw over here, would start to fly around slower. And that means, again, we're going to see less collisions and our pressure would drop if the volume remained the same. Once again, here in this situation, what's going to happen is the volume is going to decrease. And now we have these gas molecules in a much smaller area. So even though they are moving slower, they don't have as far to go to have collisions, and that will keep the number of collisions relatively constant, and we will actually see the volume adjust. So in the case of Charles' law, the way it's able to maintain constant pressure is we have an adjustable volume. So you can have like a movable piston in your container there that can kind of go up and down. And the volume of the gas will adjust to allow the number of collisions to remain the same, even though they may be moving faster or slower. Again, that volume is what kind of helps the pressure remain constant. We don't have that here because the volume's locked into place on the right-hand side there. So as you basically increase the temperature, decrease the temperature, you're going to see a pretty direct effect on the pressure. Any questions on that? And that's what we see here. This is Charles' law here, low temperature. We have a small volume of gas at a much higher temperature. We got a much larger volume of gas there, again, to allow the pressure to remain constant. Now, one of the interesting things that was seen when you sort of graph different gases in sort of a Charles law situation is you take any gas you like and you graph it with volume versus temperature, and you extend the line back to the temperature axis. They will all hit the exact same point. They will all hit the lovely number of minus 273.15 degrees Celsius. That number should look familiar to you. That is the number we use to do what? Pretty much the number we use to convert to Kelvin. And Kelvin is the guy that recognized that behavior, and he called that absolute zeros, because then if you add 273.15 to convert that to Kelvin, you get 0 Kelvin, or absolute zero. And Kelvin's the guy, again, that recognized that. And you could thank him, because what that essentially means is if you're rolling with Charles' law here, which is V1 over T1 equals V2 over T2 at constant pressure, the temperature values here needs to be converted to Kelvin. And that's a pretty safe bet for any gas law. If you got temperature, you should just like autopilot it over there to Kelvin. Yeah, it should just be like an automatic. Even if, and what confuses people, and sometimes people screw up on this, even if they give you the numbers in Celsius and want the answer in Celsius, you do need to convert it to Kelvin, put it in the gas law, and then convert it from Kelvin back to Celsius. So you do have to do that. That goes for that. Our Gay-Lussac's law here, P1 V1 equals P2, P1 over T1. That'd be good to have a temperature in that one, probably. There we go. P1 over T1 equals P2 over T2. This is obviously at constant volume. And again, the relationships we talked about on the previous page, temperature increases here, volume increases. Temperature decreases, volume decreases. Pressure increases, temperature increases. Pressure decreases, temperature decreases for our guy down here. Also needs to be in Kelvin as well. In terms of the volume, it doesn't matter the units as long as they're the same, and pressure as well doesn't matter as long as they're the same. Any questions on those two there? All right. All right, so let's try one here. A sample of carbon monoxide gas occupies 3.21 liters at 125 degrees Celsius. What temperature will it occupy 1.54 liters? Formulas to choose from. So again, if we just kind of pull out the information here, we definitely have a volume that is 3.2 liters. We got a temperature is $1.25. We're looking for another temperature here, and we have a volume that is 1.54 liters. So should hopefully point you in this direction, since there's no pressures to be used for the other two. We do have to obviously do a little 273 action there to convert into Kelvin. 125 plus 273, 398 Kelvin. Our volumes are okay. They're both in the same units. I'm going to call these guys ones, these guys twos here. So we are going to be solving for V2. Lots of underlining there. T2 there. So once again, to move across the equal sign, just going to end up in the opposite location. So I'm going to move my temperature. I'm actually solving for T2 on this case, huh? I guess I'm not doing that, huh? So let me undo that there. So in this particular case, we are solving for T2, I guess, huh? So we're solving for T2, so we're going to bring that guy up, and then our others are going to go in the opposite spots, so they're just going to switch around. So we will end up with, no, that's V2T1 divided by V1 there, if I did it correctly, hopefully. And again, that was a little messy, huh? Gonna multiply T2 to both sides, cancel. Gonna multiply T1 to both sides and cancel. And divide finally V2 to both sides there, or V1 to both sides. And we will opened up there. So looks like we did all right, hopefully. All right. So put in our numbers here. We got V2, which is 1.54 liters. We have our T1 there, which is 398 Kelvin. And we're going to divide by our V1, which is 3.20 liters. Liters are going to cancel. And we'll end up with 1.54 times 398 divided by 3.2. And it's going to give us like 191.5 Kelvin in this particular case. And we are looking for just the temperature there, I guess. So we see that in this case, the volume went down, so the temperature definitely went down into a negative number here if we subtract off, obviously, 273 from it. We'll end up with minus 273, so like negative 81.5 degrees Celsius if you kind of went in that direction. Any questions on that one there? All right, let's take a look at another one here. We got 452 milliliters of a gas. It's using a light bulb. Go for 22 degrees Celsius to 187. What is the final volume here? Pulling out the information here. We got a volume of 452 milliliters. Goes with a temperature of 22 degrees Celsius. Got another temperature of 187 degrees Celsius. And again, we are looking here for a volume. We'll call these guys ones, these guys twos. And again, once again, looks like Charles' law is the winner. We do need to do some conversions of our temperature like normal here. So a little 273 addition to each of them. Gonna get us, looks like 298 here, or 295. 295. And 460 here. Now we take our V1, T1 equals V2, T2. Here we are looking to solve for V2. So we basically just need to send that one up to the top. And that will give us V1, T2 divided by T1 is equal to V2. Put it in our numbers here. V1, 452 milliliters. T2, 460 Kelvin. Divided by 295 Kelvin there. Kelvin's going to cancel. Going to leave our answer there in milliliters. And 452 times 460. And divided by a 295 there. About 705 milliliters in this case. Once again, this is Charles' law. And we see here our temperature went up. So we would expect also our volume to go up, and it again did. It went from 452 to 705. So again, is moving in the correct direction. Question on that one there. Okay, one more here. Argon is a gas also used in light bulbs, but here we're going from 1.2 atmospheres at 18 degrees Celsius to 85 degrees Celsius. What is the final pressure here in atmospheres? We have a pressure 1.2 atmospheres that goes with a temperature of 18 degrees Celsius, going for another temperature of 85 degrees Celsius, and we are looking for a pressure. So once again, obviously there's no volume, so that gets rid of that one, gets rid of Charles' law. So Gay-Lussac's law looks like the one that we want to use. Again, some conversions of some temperatures, just like on automatic to do that pretty much. 18 plus a 273, gonna go 291 Kelvin. 85 plus 273, 358 Kelvin. Here the unit is atmospheres, and that's just going to be what our unit will be. So P1 T1 equals P2 T2 here. And in this case, we are looking for P2 if we number these. So we're going to send again our temperature just to the opposite location. That will give us P1 T2 over T1 is equal to P2. Putting in our numbers here, 1.2 atmospheres times our second temperature, 358, divided by our first temperature, 291 Kelvin. Kelvins cancel, and we will end up with here 358 divided by 291. 1.48 atmospheres in this case. Any questions on the calculation here? Again, this is Gay-Lussac's law, which is at constant volume. And that means in this case, as our temperature goes up, we would expect our pressure to rise as well. And that is what we see. Again, it went from 1.2 to 1.48. So we did see at least a rise in the pressure. Any questions on that there? All right, the last one we're going to talk about tonight is Avogadro, because he had a number, but I think secretly he just wanted a gas law as well. So when we think about Avogadro's number, we think about our friend moles, right? And in gas laws, N is what is equal to moles. So Avogadro's law is V1 over N1 is equal to V2 over N2. This is actually at two different conditions. This is at constant pressure and temperature. So at constant pressure and temperature, this is the relationship. And really the relationship is kind of as the volume increases, so does the moles of gas. And one of the kind of interesting sort of relationships that comes from Avogadro's law, in addition to obviously you could use this law like all the other laws, plug and chug in there and solve for something that's missing, is because basically the volume and the mole sort of increase and decrease together, you could actually, in a gas stoichiometry problem, look at an equation, for example, like what we see here on the bottom, and we normally look at sort of our coefficients as our sort of molecules to molecules sort of relationship, or like we do in stoichiometry more often than not, our mole to mole relationship. But if you were doing this reaction under constant temperature and pressure conditions, you could actually do a volume to volume relationship, much like you do with a mole to mole relationship. And what that can allow you to do in some cases is, for example, not have to use a gas law when you're doing gas stoichiometry, but it does need to be under these conditions, both constant pressure and temperature, and it does obviously has to be a gas sort of stoichiometry situation that's happening. So just to illustrate that here, if we take a look at this reaction here, ammonia burns an oxygen to form nitric oxide and some water. How many volumes of NO are obtained from one volume of ammonia? So, like I said before, we could go through this and do our normal sort of mole to mole relationship. But because this is at constant temperature and pressure, we can, instead of doing a mole to mole relationship, go, for example, for every 4 liters of NH3, a volume, we would have to put in there 5 liters of O2. And again, that's basically the same idea as like 4 moles of NH3 gives you 5 moles of O2. We could also say, for example, for every 4 liters of NH3, we will produce 4 liters of NO. We could also say for every 4 liters of NH3, we would produce 6 liters of H2O. And we obviously could do it for our O2 as well. 5 liters of O2 will give us 4 liters of NO, and 5 liters of O2 would give us 6 liters of H2O. So we really could do, again, just like we do a mole to mole relationship here. So for example, in this question, it wants to know how much volume of NO do you get from one volume of NH3. So I'm just going to call my NH3 instead of one volume, 1 liter of NH3. And I could do it just like I would do stoichiometry, sort of the volume to volume relationship between these two guys. And we could see that for every 4 liters of NH3, we get 4 liters of NO. liters of NH3 cancel, and we end up with 1 liter of NO. And again, you can kind of do a stoichiometry relationship here because this is constant temperature and pressure, and the volume will be the same as moles. If we were interested again in say H2O or even O2, we could also do those type of relationship. In 1 liter of NH3, we would have to put in there 4 liters of NH3 for every 5 liters of O2, right? And in this case, obviously we'd have 5 divided by 4 will give us 1.25 liters of O2 needs to be basically put in there with it. So this is a nice sort of aspect of Avogadro's law, which is, again, if you do have a constant temperature and pressure situation, you definitely can do stoichiometry without even have to worry about sort of a gas law. You could also still do it, as we'll talk about later on in this chapter. You can still do sort of a gas law sort of stoichiometry move, and you'll come out the same, but it's kind of a shortcut if you're under those type of conditions that you can do that. Question on Avogadro's law there. All right, I think we're going to lay it up